Welcome back, everybody, for another deep dive. This time we're going deep into large language models, or LLMs.
Some of the most advanced AI systems out there,
Right,
right?
exactly. And we're going beyond just like the basic stuff this time.
Yeah, going deeper.
We're diving into some fascinating research on what are called superweights.
Hmm.
They're single parameters inside these huge models that have a surprisingly large impact on how they function.
Yeah, and the research shows that just one of these superweights can be the difference between, coherent text and just complete gibberish.
Yeah, I was reading over this research paper, and I gotta admit, I'm a little skeptical at first.
Oh, yeah.
How can one number be that powerful in such a complex system, right?
I know, it's pretty wild.
Eh.
But the research shows it pretty clearly. Like, for example, they took a model called Llama 7B,
Mm-hmm.
and they gave it a simple prompt, something like, my favorite condiment is.
Okay.
And with the superweight in place, it gave a totally normal response, like mustard.
Yeah, makes sense.
But then when they removed that single superweight, the output for the same prompt just became like word salad.
So it's like the model just lost all ability to use language properly.
Yeah, pretty much.
I gotta know more about this. So how does this one single parameter cause that kind of drastic change?
So think about it this way. Each parameter in the model is like a tiny little light bulb.
Okay.
And you feed data through the model, and those light bulbs light up with different intensities.
Mm-hmm.
The superweights are like spotlights. They shine way brighter than all the others.
Uh-huh.
Those superweights, they basically amplify specific signals inside the model, and then those amplified signals have a ripple effect on the output.
Okay, so they're like amplifiers.
Yeah, exactly.
But how does that explain the whole coherent text versus gibberish thing? What are those amplified signals actually doing?
One of the key things they're doing is helping the model avoid getting hung up on those little insignificant words.
Like what kind of words?
The A is like all those really common words, what we call stop words.
Oh.
And without the superweight's influence, the output gets dominated by those stop words. So it's essentially meaningless.
That makes sense. Like if you were trying to have a conversation and every other word was
Right.
you wouldn't understand anything.
Exactly.
But this raises another question for me. So if we're talking about models with billions of these light bulbs, right?
Billions.
How do researchers even find these superweights to begin with?
So they've come up with a really clever method that doesn't actually need any training data.
Oh, wow.
It analyzes what they call activation patterns inside the model.
Activation patterns.
Yeah, basically they look at how brightly each of these little light bulbs is shining when it's processing the data.
So they're just looking for the ones that are way brighter?
Exactly. They call those bright spots super activations, and they're a really clear sign of a superweight.
Huh.
And you can actually see this visually in the research paper. Figure 3 shows a representation of these activation patterns, and the superweight location is marked by this really bright spark.
So the model is practically telling us where to look.
Pretty much, yeah.
That's pretty incredible. So let's say we found one of these superweights.
Yeah.
It's cool that they exist, but can we do anything with this knowledge? Does it have any practical implications?
Oh, absolutely.
Right.
Yeah, this has a huge impact on how we can compress these massive models to make them more efficient, which is where quantization comes in.
Quantization. Yeah, I've heard that term, but I've never really understood how it works.
Sure. So imagine you have a giant image file that you want to make smaller.
Okay.
You can use compression to squeeze it down, and you might lose a little detail, but the overall picture is still there.
Mm-hmm.
Quantization is kind of similar. It compresses a large language model by making the numbers that represent the model's parameters less precise.
Okay.
This makes the model smaller and faster, but it can affect performance too.
So how do these superweights play into all of this? I imagine that trying to compress a model with these really important parameters could mess things up.
You're exactly right. Traditionally, outliers, those values that are really different from the average, really mess with quantization because they skew the whole range of values that you need to represent.
Yeah.
And superweights are obviously extreme outliers.
So it sounds like we have this useful technique for making LLMs more efficient, but these superweights are kind of throwing a wrench in the gears.
It's definitely a challenge, but thankfully, knowing about superweights lets us come up with some clever ways to work around it.
Oh, okay.
There's two main approaches that researchers have been looking into. The first approach is called activation quantization, and it's pretty simple, really.
Okay.
So instead of trying to compress that superactivation directly, they replace it with a more typical value just during the quantization process.
So it's like they're hiding it from the compression so it doesn't mess things up.
Exactly. And then once the compression is done, they put that superactivation back where it belongs.
Wow.
And what's really cool is that this simple little trick leads to much better results than trying to quantize the model with the superactivation still there.
So a little hide and seek goes a long way.
You got it.
What about the second approach?
So that one focuses on weight quantization. And instead of messing with the superweight itself, they actually clip the other outlier weights,
Okay.
bringing those closer to the average range.
So that helps narrow down the range, making the whole quantization process more efficient.
Right.
I see. But wouldn't clipping the superweight also make the compression more efficient? Why not do that?
Well, that's the thing. They realize that superweight is just too important to mess with.
Uh-huh.
Clipping it would seriously hurt the model's performance.
Right.
So they clip other outliers, but they leave the superweight alone, recognizing how important it is.
Okay.
And this lets them use bigger block sizes during quantization, which leads to even better compression.
So they're basically fine-tuning the whole compression process to work around this one super important parameter.
Exactly.
It's kind of mind-blowing that just understanding this one tiny piece of the model can have such a big impact on its efficiency.
Yeah, it really shows how powerful this research is. It not only helps us understand how these models work better, but it gives us practical tools to improve them.
Mm-hmm.
And the researchers have actually put together a whole directory of superweight locations for some common LLMs, like Llama and Mistral and Olmo.
Wait, they're sharing the locations of these superweights?
Yeah.
That's awesome.
It's a huge help for other researchers. They can use this directory to dig in and explore all the properties of superweights, how they're different across different models, how they're influenced by training data, even how they might be tweaked to improve performance or efficiency.
This feels like a major step forward in LLM research.
Absolutely.
What if we could train LLMs specifically targeting these superweights?
Oh, yeah.
Could we make these models even more powerful or more efficient?
It's definitely possible this opens up so many new avenues to explore.
Yeah.
We might even be able to create whole new model designs optimized around superweights.
Now that would be incredible. Smaller, more powerful, and more efficient LLMs, and it's all thanks to understanding these superweights.
It's pretty amazing.
This brings us to another interesting thing from this research. The paper mentions a connection between superweights and attention sinks. Attention sinks. What are those?
Okay, so think of it this way. When you're reading some text, certain words or phrases just grab your attention more than others.
Yeah.
Well, similarly, when an LLM processes info, some input tokens seem to attract a lot of the model's attention.
Okay.
They get kind of fixated on these tokens, even if they're not that important to the meaning.
Interesting. So are they saying that superweights are causing these attention sinks?
Well, that was the initial thought, but the research seems to show that superweights and attention sinks are actually separate things.
Ah.
They're both fascinating and kind of mysterious, but they seem to be operating independently.
So 2 more mysteries to solve. That's AI research for ya. But I'm curious, what do you think about the big picture here? What does the discovery of these superweights tell us about LLMs and AI in general?
Well, it's early days, but I
Mhm.
think this research gives us some really valuable insights. For one thing, it suggests that these really complex models might actually rely on a relatively small number of really important parameters for their core functions.
So instead of trying to make sense of billions of parameters, maybe we just need to understand a few key ones to really get how these models work.
Exactly. And secondly, I think it shows us a certain fragility in these systems.
Right.
If just one parameter can totally change how a model behaves, what does that say about the overall stability and reliability of these things?
That's a great point, especially as these models get more powerful and more integrated into our lives.
Right. And it also brings up some ethical questions.
Like what?
Well, if someone could manipulate just one parameter to drastically change the output, what does that mean for biased misinformation? The potential for misuse.
Those are some big questions we need to be asking.
Yeah.
But maybe that's a discussion for another time. Yeah.
For now, I think we've given our listeners plenty to think about.
Yeah, it is a lot to think about. But before we go too far down that rabbit hole, let's come back to the research you mentioned that the researchers put together, that directory of superweight coordinates.
Right, yeah. It's like a treasure map for anyone who really wants to get their hands dirty with this research.
So for those listeners who want to go beyond just listening to this deep dive and really dig in, we'll make sure to include a link to that directory in the show notes.
Definitely a great resource for researchers, developers, anyone who just wants to see how these models work under the hood.
As we're talking about this, I can't help but think about the potential applications of all of this.
Yeah.
Imagine being able to use this knowledge to develop AI assistants that are more efficient and more powerful. You know, tools that can help us with anything from writing to research to even like creative problem solving.
The possibilities are really endless, and it's not just about making these models better. It's about understanding them on a
Yeah.
deeper level.
Yeah.
By finding and studying these superweights, we're learning about the core mechanisms that make these AI systems work.
It's like we're taking apart a really complex machine piece by piece and figuring out what makes it tick.
Exactly.
And with each discovery, we're getting closer to understanding the nature of intelligence itself, maybe even our own.
It really is a fascinating journey, and this research is a big leap forward. It's given us this powerful new way to look at these models and the tools to really explore them.
Well, everybody, it looks like we've reached the end of our deep dive for today. We've explored the world of superweights, uncovered their hidden power, and thought about what they mean for the future of AI.
It's been a fun one. Hopefully you come away with a new appreciation for how complex and amazing these systems are, and maybe even a few more questions to ponder.
And that's what it's all about, right? Asking questions, seeking answers, and always diving deeper into the unknown. Until next time, keep exploring and keep learning.